Hello and welcome to this section of Calculus 1, Extra Practice with Integration. Here we're going to talk about properties of the integral. So again, we're working our way forward, teaching what the integral is, what the fundamental theorem of calculus is. Here we're going to cover some very important properties, mostly so you understand the terminology, and then we get into the subsequent sections, we'll just start working problem after problem. But I need to cover this introductory stuff so that you're not scratching your head, like what did he mean when he said that, for instance. So let's go and talk about a few important properties. These are things that are in your books, but they're usually buried. I'm going to try to show you all kind of rapid fire what these properties are. They're all, by the way, very, very, very easy to understand. So if we have a graph of x and f of x, like we've been talking about this whole time, and if we have some function, like this, that we're interested in between a and b, so this is a right here, so this is the area under the curve that the integral is calculating, right? One thing I didn't tell you, but that looks pretty obvious at first glance, is that this is positive area. In other words, if I calculate the area of this the stuff underneath the curve, I'm going to get a positive number. That's all I mean when I say positive area. Now let me show you another example. So let's see here. This is f of x, and this is x, and here's another graph going down like this. Now let's say we have something like this. This is another graph, right? But it's below the x-axis. And again, from A to B, this would be the area that you're calculating in this case. If the graph lies below the x-axis, so you're always calculating the area between the function and the x-axis. So wherever it lies, that's what you're getting. You might be able to guess, since I'm going through the point of showing you this, that if the area lies below the x-axis, that's a negative area. Now this is nothing mystical to be concerned about. All it means is it's a definition thing. It's how we're calculating the area that causes this to happen. If your function lies below the x-axis and you calculate the area, you're just going to get a negative answer. When you do the fundamental theorem of calculus and evaluate the top limit minus the bottom limit, what you're going to get is -5 or -3 or -10 or something like that if it's underneath here. So if your graph is above the x-axis, you'll get a positive area. If your graph is below the x-axis, you'll get a negative area when you calculate that definite integral. And just so you know, if for whatever reason, we draw another one here, kind of a small one here, if for whatever reason your graph, part of it is above the x-axis and part of it's below the x-axis like this, let's say you're calculating, here's let's say B and let's say A is the axis here, then what you're really calculating is you're calculating the area here and the area here. So when you look between A and B here, if A is the origin, x is equal to 0, and B is over here, like x is equal to 10, part of your function lies above the x-axis and part of your function lies below the x-axis, then when you do the integration, you don't have to think about it or worry about negative or positive area. You don't have to worry about it, but I'm just telling you that the area that you calculate in this region is going to be positive, the area that you calculate in this region is going to be negative, and when you do the integration from A to B, it's automatically going to take care of all that stuff. So for instance, if the area here just happens to be exactly equal to the area below the x-axis, then you're going to get 0 for an answer, because the positive areas and the negative areas will cancel out. So just kind of keep that in mind. If your function crosses the axis, then you're going to have some negative areas and some positive areas. The integration from A to B is a sum total of the algebraic signs of all of these areas between A and B. All right? So that's what I want to talk about there. The next thing I want to talk to you about is what if you had something like the integration of two functions added together? So f of x plus g of x dx. What do you think would happen? If I'm actually integrating two functions that are summed together, what you're going to get is the integral of f of x dx plus the integral of g of x dx. So this integration symbol, you can kind of think about it as distributing itself in. By the way, it's exactly the same thing for derivatives. If you have a derivative of two functions summed together, you just take the derivatives of the individual pieces. So you're just taking the integrals of the individual pieces and summing together the answers. And the exact same thing holds if you have limits here. If I had limits of integration, let's say this integral was from a up to b here, then over here I would have a to b, and over here I would have a to b. So indefinite or definite integrals doesn't matter. You're going to get the same answer either way. All right. Let's change colors here and say, what if I have the integral of a constant c, this is a number, times f of x dx? What do you think you're going to have? Well, if you remember back from derivatives, if you have a constant times a function and you take the derivative, then all you do is you take the constant outside and then handle the inside. And that's exactly what happens here as well. So if you have a constant and you're multiplying by a function like 5 times x squared or something, then the 5 comes out, and then you're still taking the integral of the x squared or whatever your function was there. And this is very common in calculus. When you have these linear functions like this, the constant can come out. Now, if this were a definite integral and you were integrating from a to b, then the same thing holds. You would still be integrating from a to b. The constant would come outside of the integral. So indefinite or definite doesn't matter. All of this stuff holds true. Now, what do you have if you had something like the following? Let me show you something neat. What if you had, this is the fourth little property here. What if you had the integral from a to b of f of x dx, right? What if you, actually what I want to show you is this here. Let me flip this around. Instead of from a to b, let's do from b to a. So in other words, typically we're doing from a to b. What if I flip the limits of integration and go from b to a, which is a little bit weird when you think about it, but don't forget, these are just limits of integration. So here I have put the a for the lower limit and b for the upper limit, but what happens if I want to do an integral where I flip these guys around and I just put the lower limit here and the upper limit here? What do you think is going to happen? The answer is it's going to be the negative of the integral a to b f of x dx. So in other words, what you're trying to say here is, if I flip the limits of integration and just flip the numbers around here, then I get the exact same answer as if I had done it the other way, but I just have to stick a negative in front. So if you flip the limits of integration, you're going to get a negative answer as to what you would have gotten originally. So it's very simple to understand. And the reason all this happens, I think this is a good place to give you something concrete. Let's just show you real quick. What if I had integral from 3 to 4 of the function 2, which is a constant, super easy function to deal with, dx. The antiderivative of 2 is 2x, because if we take the derivative of this, we get back what we started with, and we're evaluating from 3 to 4, lower limit to upper limit. So what we have is 2 times 4, always evaluate the upper limit first, minus 2 times 3. Evaluate the lower limit here. So what you'll have is 8 minus 6, which is 2. So that's the answer. Okay, so that is the answer there. Now, let's go and flip the limits of integration. So instead of 3 to 4, let's just, for giggles, let's do 4 to 3 of integral 2 dx. So this is going to be the same antiderivative, 2x, but I'm going to evaluate from 4 to 3 this time. So here it'll be 2 times 3. I always evaluate the upper first. 2 times 4 down below. I think you can see where this is going. I'm going to have 6 minus 8, negative 2. So all this property is trying to tell you is if I have an integral and I get an answer, and then for whatever reason, if I flip the limits of integration around, I'm going to get the exact same answer, but a negative sign there. Okay, not too hard. How is this useful? You know, it just comes into play when we're learning more advanced integration techniques. Sometimes when the proof is done in your book or when we're solving some problems, sometimes it's useful to flip the limits of integration around, and then you just need to know if you ever do that, stick a negative on the answer, because that's basically what's going to happen. Now what I want to do next is talk a little bit more about something so very, very important. Okay, and that's called the constant of integration. So you see this in books. A lot of students don't understand where it comes from or why it's important. So I'm going to actually label this because this is very important. The constant of integration. I can't stress enough how important. Some of these other things are kind of nice to know, but this one's really, really, really important. What if I had the integral of something, some function, call it 4 this time, dx. Now, what have we said before? We said the antiderivative of 4, we've said many times that it's 4x. The reason that it's 4x is because if we take this guy and we take its derivative, then we get back what we started with. And I've kind of led you to believe all along that it's just that simple, right? But the truth is that it's not quite that simple, because if you think about it, this is the answer, but I can add to it any arbitrary constant I want. Any arbitrary constant I want. I can add 10, I can add 15, I can add 49, I can add negative 37, I can add 2/5, I can add pi. Any constant I want, I can add to it. And this constant, whatever I add to it, along with the 4x, is really the answer to this guy. And the reason is because if I take 4x plus a constant and take its derivative, I'm going to get, what is the derivative of 4x? It's 4. What is the derivative of a constant? Well, it's 0, right? So what I'm trying to say, this is an arbitrary constant of integration. I've kind of lied to you a little bit and said, well, the answer is 4x. Really, the answer is 4x plus any constant you want, all right? So what this really means is that anytime you have an indefinite integral here with no limits of integration and you get an antiderivative, there's really an infinite number of answers. And I'm going to say that again because that probably hits you like a train, you know, but it's true. There's really an infinite number of answers to this problem. The reason is because, you know, my answer I could choose, I could have 4x plus 2. Well, what's the derivative of this? Derivative's 4. I could have 4x minus 9. What's the derivative of this? Well, the answer is 4. Because the derivative of these constants are always going to be 0. What if I had 4x plus 7/5, some crazy fraction or something, take the derivative? Well, the answer is still going to be 4. No matter what constant I put in here, when I take the derivatives, because constants and derivatives, you know, when you take the derivative of constants, you always get 0, then basically any constant you add into the answer just disappears and doesn't matter. So the bottom line is, and this is so very important, when you have an integration of something that with no limits like this, which is called an indefinite integral, then what you're going to get is your answer plus an arbitrary constant c, and you always need to write that down in your answer. So on a test, if you're asked to integrate something and there's no limits here, then you need to put the antiderivative plus c. The c means that you understand that there's an infinite number of solutions. Many, many, many variations of the answer can be given out, which will always yield when you take the derivative back what you started with. It doesn't mean that it's crazy or far out or anything. It just means that literally there's an infinite variety of answers all based on this antiderivative that can be chosen with that arbitrary constant there to give you back what you started with. So you always need to write that down. If you don't write plus c down, then you're probably going to get some points off on your test. So it's very, very important for you to do that. Now let me pause from that and show you what it looks like when you have a definite integral. And then we'll kind of round out this section here. What if we had integral from 1 to 2 of 4 dx? So it's the same exact integral as before, but we're going from 1 to 2. And I said, well, what is the answer here? We said it was 4x, right? And now I'm telling you there's this constant of integration. So let's just go ahead and include it in the answer. 4x plus c. That is our antiderivative, right? And we still need to evaluate it from 1 to 2. So let's see what happens. All right, so then we evaluate this guy, 4 times 2 plus a constant. Don't forget this is the entire answer, so I need to evaluate this entire answer at the upper limit of integration, minus evaluating the entire answer at the lower limit of integration. So the plus c is coming here because I'm evaluating this at 2, and I'm evaluating this function at 1, right? And I'm doing the fundamental theorem of calculus to see what happens. All right, so let's see what happens here. So inside of this guy, I'm going to have 8 plus a constant. And here I'm going to have 4 plus a constant. Now watch carefully what happens. 8 plus c, here's a minus sign, so I'm going to make it minus 4 minus c. Now look very carefully what happens. This constant disappears with this constant because it's plus c and minus c. So they subtract to give you 0. So what you're going to have is 8 minus 4, which is going to give you positive 4 as your answer. Positive 4 is your answer. So what am I trying to say here? What I'm trying to say here is when you do these integrations, all right, when you do these integrations, you really always get a constant c in your answer. But when it's a definite integral, when you evaluate at the limits of integration, right, the c drops out because you're subtracting it from the upper limit and the lower limit, so the c disappears. So that's why whenever you're doing these definite integrals, you don't really have to mess with c too much, because definite integrals, it doesn't ever arise in your answer because it subtracts out. But when you have an integral with no definite integration, you have to keep c in your answer to be explicit. So for instance, if on a test, your teacher says, what is the integral of 2 to 3, the function is 2 dx. Well, see, this is a definite integral. So you say, well, the answer is 2x. You don't need to put plus c here because you know it's going to disappear. 2 to 3, right? And then you go evaluate at the top boundary here, and then you evaluate at the bottom boundary here. 6 minus 4 is 2, and this is the answer. So I want to just make sure you get this because it's so very important. If you have definite integration, right, definite integral with limits, then here when you find the antiderivative, you don't really need to put plus c, because I've just showed you a minute ago that if you do it, I mean, you can do it, there's nothing wrong with it, but you don't have to, because even if you do it, this constant just subtracts out and it always disappears. So if you have a definite integral, you don't have to worry about the constant of integration. And that's what trips people up a lot. Sometimes people, when they study integration the first time, they learn about this constant of integration. They're like, why do you put it on this problem here, but you don't mess with it when you have these other problems here? Well, the answer is very clear. There's always a constant of integration, but if you have a definite integral, it always subtracts out, so you never see it. So if you have definite integrals in your test, what everybody does really is they just forget about the constant of integration because it doesn't matter. You evaluate the top and the bottom limit, you get a number. But if you have a problem where you have indefinite integral, then you have to find the antiderivative and you have to include this constant of integration in your answer. And if you don't, you're going to lose some points. Some quick, easy points that you could easily get out of your test. So that concludes this section on properties of the integral. We need to kind of take a little baby steps in the beginning of a new topic before we can dive into working tons of problems. Because if I don't do that, then you'll inevitably wonder what I'm doing sometimes when we get to the problems. So we have to take this one step at a time. Basically, the first property of an integral is basically saying that if you have area or a function above the x-axis, you get positive area. If you have a function below the x-axis, you're going to get negative area. And if you have a function that has some part of the function above and some part below the x-axis, a portion of the area will be positive, a portion will be negative. The integral takes care of adding it all together. The final result you get is the algebraic sum of these different areas. The second property says if I add two functions together, then I just take the integral of each function separately and add the results. This is just like derivatives. You take the derivative of each term and you add the terms together. Right? This function says if I have a constant times a function, and I'm integrating that, then I can pull the constant out and then integrate the function. This is exactly like derivatives. If you have a constant times a function, you take the derivative, constant comes out, and you take the derivative of what's left over. The next property says if I have a function and I'm taking the limits of integration and I flip them around for whatever reason, go from b to a, then I'm going to get the exact same answer as the integral from a to b, but I'm going to have a negative sign on the front. And I actually did two examples to show you that you actually get exactly the same answer with a negative sign. And that basically boils down because we're doing subtraction here in the fundamental theorem of calculus. And then the final property of integration is the constant of integration. Anytime you do an indefinite integral with no limits like this, you get an answer and you have an arbitrary constant. And that's because when you take the derivative of the answer, no matter what constant you make up, you can still arrive at the original function. If it's a definite integral, then yeah, you can do the constant of integration if you want, but it doesn't matter because it always subtracts out in your answer. So if you have a definite integral, typically what you'll see is the antiderivative here without any constant of integration, and then it's just kind of implied that the constant of integration doesn't matter when you have definite integrals because of what we've talked about. So make sure you understand these properties. We'll revisit them a lot as we go forward. And make sure you just kind of get a nice understanding of what we're doing here. Make sure you can go back and follow the logic of everything. Follow me on to the next section where we will finally kind of roll up our sleeves and learn about our first class of functions that we can integrate in calculus.